What's up? Okay, so I had a question just before class regarding problem 2, right? Wait, Max?
Sorry.
Was it regarding problem 2?
Yes, sir.
Okay, so problem 2, part 1, how much work in joules is done by the friction as the sled moves down the hill. So you have to calculate, of course, what the force of friction is. And you notice the force of friction is the opposite direction to the distance. So 180 degrees, cosine 180 degrees is negative. It gives you negative value.
Right.
And you have to go through your free body diagram to find what the friction is. And then you have your how much work is done by the rope. So you have to use the tension force. Once again, the angle between those is 180 degrees, so it's negative. Then you have what is the work done by the gravitational force? Well, because I broke things into components, I know the gravitational force that is parallel to my motion. Now, notice I have a negative sign there for the x direction. My motion is in the minus x direction, so it's in the same direction. And so I just have mg cosine 30 degrees, the amount that's parallel to motion, times the distance. Remember, work is force times distance parallel, so that's why I'd already broken them into components. I just used the parallel component there. And then we have the final part, which is what Max asked about. Now, before I do that, and of course, David, I just asked him these questions as well. It did not ask you about the work for one of the 4 forces. Which force did it not ask you about the work for? The normal. Why did it not ask you that? No.
There's no movement in that.
There is no motion parallel to the normal force. Hence, it cannot be doing work. Sometimes people will say normal force can't do work. Well, that's not true. I put this boogly on my hand. Right now, the normal force is doing no work. Still doing no work. Now the normal force is doing work. Right? So an elevator, the normal force, keeping you from going through the floor, does work on you as you go up. So that statement of normal force can't do work is not true. But if you have a stationary surface, then the normal force can't do any work. So then we have adding them all up, because the network is just adding them all up. And the reason Max came up to me all perplexed is because when you add up the numbers rounded to 4 decimal places, because that's all the textbook keeps, you get 6 or something like that.
Yes.
But it's not right. It's not right because of rounding off. So let's go back and look at the beginning of the question. Suppose a ski patrol lowers a rescue sled carrying an injured skier with kind mass, blah, 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 at constant speed. That at constant speed is actually how you're supposed to answer this. Because the work-energy relation says that the net work is equal to the change in kinetic energy. If it's at constant speed, how much is the kinetic energy changing? Constant speed, kinetic energy, what's the equation for kinetic energy? I know you've only had it for 2 days. I introduced it on Monday. 1/2 mv squared. So if v is constant and m is constant, what's 1/2 mv squared? It's also constant. So the change in it, otherwise known as the net work, is 0. And so for that one, the correct answer is simply 0. And Max thought, I put that in. So, yeah, it was round off error. And because it doesn't really honor sig figs, it has no way of correctly dealing with an answer that's 0 when you have round off error with adding things up. Which is unfortunate, right? Okay, good homework question. All but one of the homework questions I went over, they're already there on OneNote. Yes, ma'am.
I have a question on the lab.
On the lab, yes.
The question number 4, PC4, 3, the one where you calculate your kinetic and your gravitational something.
All right, let's all run to our laboratory. All the calculus in the lab guide. Okay, describe how you could have determined the maximum height above the trampoline, assuming that maximum speed occurs the moment your feet leave the trampoline, from the speed at the moment your feet leave the trampoline and your elevation at the same instant. So this brings us to the work-energy relation again. The work-energy relation, net work is equal to change in kinetic energy. But work can be broken up into two pieces. We can have the non-conservative, that's the one that has to do with friction that's taking energy away from us, putting it to something else. And the conservative, where it's going to return the energy. Once you're up in the air, assuming no air resistance, just assuming no air, what force is acting on you? We say you're in free fall, what force is acting on you? Gravity. Gravity is conservative, so you should have a constant energy. So when you leave the trampoline, you have kinetic energy. When you get to the top, the kinetic energy is going to be zero. Where will all of that kinetic energy have gone if energy is conserved? Into gravitational potential energy. So you just say the total energy I have at the moment I leave the trampoline is the same as the total energy I have at the highest point where V is zero. You calculate what the H would be. Did you get that? Now, on the topic of the lab, I hope you had a good time. I hope you did learn some things. I'm sorry for those of you who didn't do the riding around on the little zip line thing, as they called it. Obviously, it's not a zip line, but you're hanging from ropes. Then there's the analysis part. And I did make some corrections in this, but just to get you started, remember that you need to download this file from Moodle. I moved it up so it's with the other lab stuff instead of down lower. And you need to download this software from the internet because this software is what that module runs on. So you need to download both of those. And of course, I have a site license, which, excellent, which here's the site license key right there. So you can put it in your computer and run it forevermore in case there's some reason you need to. Like in the future, you want to analyze video or something else. Okay, so just want to make sure because we had some people who downloaded one but not the other, and you can make your own graphs, but it'd probably be quicker just to, yeah. So lab report, just like everything else. Yeah, I accidentally looked at a different one and it said something about your scientific method here. There was no scientific method part you had to do for this, so you have still your procedure and that kind of stuff to write up for the lab report and answering your questions. Any questions about lab?
So the procedure pretty much be you drove to trampoline place, jumped, video, the end, left.
Okay. Your procedure would be videotape jumping on trampoline with, a meter scale. And by the way, those ropes, it's hard to get them straight. I probably should weight them or something because it turned out that I had, 10.8 was my acceleration of gravity from analyzing my jumping. And of course, that's not right. Why is it wrong? It's not because gravity was different there. It's because my scale for the meter, it was a little curled, and thus I have a shorter distance per meter, and thus it's calculating a higher acceleration. But you took the video and then analyzed by identifying the position of my nose in each frame. Also, that was a problem in my analysis because when I was going up, I kept my face pointing forward like you're supposed to. Coming down, I looked down to see where I was going to land. And of course, that shifts the position of the nose by a little amount. So that also caused some error in my data. Those are the kind of things you talk about, in your data, when you're doing the data section, you have your data and the problems. Yeah. So you understand, you have collection and the analysis that both need to be there in the procedure still. My brain perfectly there. Just can't remember where it's going. We're in the same boat. Excellent. You got a question?
Yeah, for like the homework thing for problem 3, part C, I was confused as to why we weren't like multiplying our MB plus MW just by gravity, and then like adding that to what did we add? It was like we like did it a certain way for like B, and then we did it like the same way part C, but it wasn't right, and I wasn't sure why.
Okay, so part 3, you have a farmer who is foolishly pulling up with a much greater force than the weight of the bucket. If he's pulling up with the greater force than the weight of the bucket, what's happening to the bucket? It's accelerating. It's not just going up, it's coming up faster and faster and faster. So when it gets to him, it's going to go shooting out and the water's going to be lost everywhere. So he's being unwise. Our equation is work is equal to force dot delta x, right? The parallel components are force delta x cosine theta. So for the farmer, we have the force, 53 newtons, and it's the same direction, 53 newtons in mine, and it's the same direction as the motion. So it's just, in my case, 53 newtons times 14 meters. Then for the next one, you have calculate how much work the farmer does in the bucket, calculate the work done by gravity. Well, then the force of gravity is this mass times G.
Times 14, like times the height.
And then times 14 again.
So we did that and it wasn't right.
If that's the case, come show me. Because, yeah, it should be just that. And so if that's not working out, either there is...
Yeah, that was like my first try.
Yeah. So after class, let's talk about it.
Which is what I got through my first one.
Okay. Now, what we're doing in class today is problems. We do a lot of problems in this class, don't we? We have a lot of problems. So we're dealing with energy. We learned about work and potential energy and kinetic energy and the work-energy relation on Monday. We did some practical work with it on Tuesday. And now we're going to do some problems. Now, I have there a picture of a woman in a swing or a car going up a hill. Imagine the car is a coaster. It has no engine. It had to be going really fast at the bottom. What kind of energy would it have at the bottom if it's going really fast? Kinetic energy. As it goes up the hill, what's happening to energy? It's converting from kinetic into potential. Now, that picture actually says something different. That picture's talking about, okay, it has a motor. Gets up to the top. It's high centered. It's not going anywhere in that picture. But let's say that it's still moving at the top. What kind of energy does it have at the top? If it's still moving. Has both potential and gravitation, potential energy and kinetic energy. And then as it comes down, what's happening? Potential energy is being converted into kinetic energy. So as it drops, the potential energy is dropping, the kinetic energy is increasing. Now, the reason it has energy in and energy out is when you do this in your car, you generally say, I'm going to stay at 60 miles an hour the entire trip or whatever. And so as you're going up, you're having to put in more energy because kinetic energy is staying the same, but potential energy is increasing. And then when you come down, you're pressing the brakes because you've got to decrease energy or you're going to speed up a lot. One of the demonstrations I usually do, I was going to go buy some of those little S things so I could use my bowling ball, is to stand over here with the bowling ball at my chin, let it go, swing over, and come back. When it comes back, what's going to happen?
It's not going to hit your face.
Not going to hit my face. Got two scars here. No, different volleyball. Actually, one's for volleyball, one's for something else. It's doesn't matter. It's not going to hit my face. Why won't it hit my face? Okay, you said energy is conserved. So if energy is conserved, if it starts at my chin, where is it going to end up when it comes back? At my chin, because it started with zero kinetic energy and potential energy of mgh. Goes down, comes up, should come to the same height. But the fact is it's not even close. It'll be like an inch away from my chin. Air resistance. Air resistance is a non-conservative force. It's not going to give me energy back. It's just going to take it away. And so the energy is dropping because of air resistance, so it doesn't come quite as high. If there wasn't air resistance, it would keep swinging really long time until other things like, whatever flexing we have up there dissipate the energy. So if we did the same thing or in a vacuum chamber, it would keep going for a very long time. You're never going to have a system where you can have it, nothing that's giving you a non-conservative. For our purposes, though, we say it's non-conservative if there's, no friction, basically. So let's get into doing some problems. First, methodology. You have done problems that had work, that had some energy, but you really haven't done work energy problems yet because we haven't gotten to the methodology. That's today. And it's what you're going to be doing for Friday. So first, draw your diagram of the situation. It's no longer the same as a force problem, so you're not necessarily drawing a free body diagram. Sometimes you want to draw the forces, sometimes you don't need to. Second, calculate the kinetic and potential energies at the start and end of the problem. Now that's very different from anything we did with forces. You calculate the beginning and ending states. 3, determine if there are non-conservative forces like friction. If there's friction, well, life got harder for you. Of the 3 problems we're going to work in class, the last one has friction. If there's friction, you have to calculate the work done by the friction or any other non-conservative force. And then you use the work-energy relation in the form that work non-conservative is changing kinetic energy plus changing potential energy. So let's do this. Problem number 1. We have a roller coaster, and it goes down a hill, comes up a little, and notice the bottom line there. If work done by friction is negligible. What does that mean? That means work non-conservative is 0. So for this problem, this line here tells me that I can set this equal to 0. It's the easy case. The figure's already drawn, so I don't need to draw the figure. So what do I do next? Find the kinetic and potential energy at the starting and ending points. So here's the start. That part was pretty clear. So what's my kinetic energy at the start? Yeah, it didn't actually. Oh, yeah, it did. It says it right there. Okay. I was looking in the words. Isabel. Because the work done by friction is negligible. The work done by friction is the work non-conservative. Now, just to be clear, it's not only friction. If there was somebody pushing it, the person's pushing would also be non-conservative. You can't put the energy back in the person, for instance. Or if you had a machine that was making it move, you can't push on the machine and have it turn air and pollution back into gasoline. Right? So those are non-conservative examples. But friction is the dominant non-conservative one we deal with. So the work non-conservative is all non-conservative things. There are none of the other non-conservative things, and it says that friction is negligible, hence work non-conservative is 0. Does that work? What's that work? That's a bad choice of words. Okay, so kinetic energy initial. If speed initial is 0, what's the kinetic energy initial? That's right. Oh, by the way, did you guys know? Okay, this is off topic. This is now considered a racist symbol because some guys jokingly said that racists use this, and these racist people weren't smart enough to know it was a joke, and they started using it. Yeah. What? It was just this week that it was officially added to the Anti-Discrimination League's hate symbols. Huh? I can't hear you. Oh, okay. Yeah, defamation. Yeah, you're right. Anyway, I saw a funny meme talking about all these, Hillary Clinton, Barack Obama using hate speech because they, of course, use the OK sign. Anyway, so on with this. We have the kinetic energy initial. What about the potential energy initial? There is a question you have to answer before you can answer that. Where is our reference point for potential energy? It's completely up to you what you choose. The problem will work out the same no matter what you choose. You could choose the reference point to be 3.67 meters above the starting position. Why would you do that? Because you're a glutton for punishment. So there's a couple obvious things to choose. One is say, well, let's say the starting position is 0 height. And then the final position would be minus 20. Or I could say the final position is 0 height and the starting position is plus 20. Or I could even say the lowest point it goes is 0 and the starting position is 25 and the ending position is 5. Any one of those is more sensical than making up a random number. I tend to choose the final is 0 just because that's going to give me a 0. Although in this case, you know what? I have 2 potential finals. I'm going to choose the top as 0. It doesn't harm anything. So I'm going to say potential energy initial is 0. So that means this is height equals 0 up here. So now at this point, kinetic energy 1. What's kinetic energy 1's equation? 1/2 mv1 squared. What about potential energy 1?
mg times
Okay.
which h is negative 25.
So I'm putting that in now simply so we don't get confused later on because h is a generic term, but yet here we'd say, oh, h is, So just to make sure we're clear on that. And what about here? Kinetic energy, I'll call it 2. What's the kinetic energy equation at the finish? Squared. And potential energy 2? Okay, so once again, I put that in explicitly here so we don't come back and forget what we have. Notice where I didn't know the speed, I just put the equation. Where I knew the values, well, I normally leave it in variable form up till the end, but man, this time I did. So let's get to work. We have a figure. We've identified the before and afters. We've identified the non-conservative. There's a certain order, but at this point, I'm just saying the things we've done. And so now, let's find the speed at position 1. So I'm just going to do 0 is equal to change. Change is always final minus initial, right? So that's going to be kinetic energy 1 minus kinetic energy initial plus potential energy 1 minus potential energy initial. Then looking at the work that I've already done, kinetic energy 1 was 1/2 mv1 squared. Potential energy initial was 0. Potential energy 1 was minus mg times 25 meters. I just brought the minus sign outside of the parenthesis there. Minus 0. That's why I chose the top to be 0 because I'm going to have it in every calculation to make life a little simpler. And now just taking out the zeros. And notice that there's an m here and an m here. Since it's 0 on this side, I can cancel the m. I'm dividing everything by m. 0 over m is still 0. And what I'm left with is that equation. I'm solving for v, so move the g across and multiply by 2. Well, we could probably all do, I'll write it out, 9.80 meters per second squared times 50 meters half of 9.8 is 4.9. I already multiplied by 2. It was 25. Sorry. And so this is going to be 490 units meters squared per second squared. So if V1 squared is 490 meters squared per second squared, then what's my speed? Hot tip, it's not 70. Nor is it 7, sadly. Now you see the 49, you think square root of 49. What is V1 equal to?
Meters per second, so that's
Square root of 490.
not 70.
Yes, that's a. So I have 490 square root. 22.13.
Yeah.
I really only have 2 significant digits, so I'm just going to put the 22. And then technically it has a plus or minus there. Could be going forward or backward. Although I'm pretty sure it's going to be going forward at this point.
I would hope so.
Next.
So all we needed to find velocity was a height. Technically.
Yeah. Now, how is this different from doing it with forces?
There weren't any forces really.
Well, there are forces, right? There's the force of gravity. There's the force normal. And if we were going to try to solve this, of course, the force that's accelerating is the force that's parallel to the track, which at the top was 0. But then as it goes down, as it changes slope, the force accelerating, it's changing. And so you'd have to do a lot of annoying calculus to get to your answer using Newton's second law method. Using work energy, we find that the path doesn't matter if there's no friction. It's just starting and ending points that matter. So it's the same answers you would have had if you just dropped it, but it technically would be incorrect to do the calculation if you just dropped it because that's not what our situation is. But using work energy, we get that simple equation. And I say simple, it really is simple. I'm trying to explain things and doing a lot of extra things to make sure that you see the process and don't just see, oh, he did some work and got the answer. So that's the speed at the lowest point. What can you tell me right now about the speed at the finish line?
Calculating it now.
Well, no. Before you calculate it,
It's going to be less than.
it's going to be slower because it's at a higher elevation, which means you have more potential energy, a little less kinetic energy. So David is already solving it. Notice by comparing the equations, the only difference between the final and the initial is minus 20 instead of minus 25. And so doing the final case, I'm going to have fundamentally the same equation except for this here, instead of 20, that's 25, it's going to be 20, which means this will be 40 instead of 50. And so I'll have 40 times 9.8 that I can't do as easily in my head. I mean, I could, but it would be
392.
Okay, be 392. I don't have to do it now. He told me the answer. And so
You get about 20 meters per second.
there, I put the 2 times 20 just so we be clear. That's where the 40 came from. And so what'd you get?
19.8 meters per second.
So plus or minus 20 meters per second. And once again, we can be pretty confident it's going to be going, forward, not backward. So that's how work energy problems work. They're not super hard. In fact, they're easier than what we've been doing in the past. You just have to go through the process. So let's go through the process. Now on this one here, we've already done part A. That is, we calculated the speed the roller coaster would have to have. Just to reiterate that, especially because I goofed it up the first time, centripetal acceleration is equal to v squared over r is equal to 1.6 g. And I'll put v subscript top. So v subscript top is equal to the square root of 1.6 rg, which of course just gives you a number. And for our purposes right now, I'm leaving it at that. Now the question is, how high above the top of the loop must the roller coaster start? So the roller coaster's up here and it starts at some h above the top of the loop. So how high must that h be above the top of the loop to achieve that speed? So now I want you, as a table, to figure it out. All right. Sarah knows what G is. So if you have a question, there you go.
Yeah, so how high does the hill have to be in order for it to? So it starts to rise. So potential and probability.
Well, I started with the equation for the work energy. So I had
And then,
Do we know what the R is?
four terms, but two of them were zero.
Raise production in the
All I know is
first.
I'm gonna hit them on.
Two of them were zeros. And one of them had E1 in it, and one of them had almost, I knew height divided by
What?
Do you use this?
cancel the ends.
What you see?
Oh, what do you
You wanna do what? Max?
So, like
You see
the
compressor?
14,
I'm not even.
I got that.
Yeah, so that's what you're doing right here. So
then, the radius be the same.
Wow.
The radius
You gotta say that.
equals.
R is, yeah,
Let's say.
it's 14 meters.
Yeah, we gotta call it.
Now we're solving for the height.
Oh.
What is the mass of the barge?
Isn't it?
It is completely irrelevant.
Just kidding.
You're right, it
Is
is.
it both kinetic and potential?
Yeah, they do.
Okay. So I
Equals
cancel
on
out.
so they cancel.
You're saying I change it.
I don't have the number of problems.
Maybe.
Calculate it myself.
Wait, they cancel out, which means the two of them are equal to one, right?
What was that?
Is that two of them equal to one?
Are we supposed to use this equation again?
Yes, that's what.
That's how they cancel out.
Remember the steps. She has them on her qualification.
Actually,
Seriously, dude? Well, you have it all with you.
that is.
I wrote all of it. Because I'm together.
So that means your equals.
Don't say that. Don't say it.
Three
You're doing this.
squared minus three. No. What'd you get? Is that not what we're solving for?
What is the speed of the locomotive?
Yes. We're solving for the end. Solving for the
Starting
end.
speed will be zero.
No, you're solving
Yeah.
for.
Where's the H?
The H.
In this, in the MGH. You're gonna divide by M. Okay.
Yeah, that's what that is. That's ingenious.
1.6
Okay.
times 4 times 1.6 times 9.
I don't know how to do
Wait,
calculations.
You gotta change that in
Remember, he did just have an answer.
Oh, no. The downward acceleration of the car is 1.6 plus.
That should be right.
Read the whole last one. It says the downward acceleration of the car is 1.6. How much is
What'd you get? I got 11.2.
Should be 5.9.
That's what I got.
I got negative 11 points, right?
No, because it was negative here, and then this would be negative as well. So then it cancels. When you minus this over this, and then this is the number put down. No. I have
Velocity.
so it's for negative nine.
Acceleration. It's velocity. Oh, wait, that was where. This
That
velocity.
Oh, I don't know then. It can't be negative, so. Yep.
What did you say to do?
I just
For that?
Yeah.
I'm like looking for no crazy. The kid doesn't really want to see your bro. I'm trying to stay your bro. I just want to feel your bro.
So you
So that's why we have
your
those.
potential energy and kinetic energy at the moment you leave the trampoline.
And he wants to find that.
And you say that's the total energy at the top as well.
You're
And so how much higher should those have to go for
acceleration. So it's still just a magnitude expressing as gravity.
No. Right, and I did, but I did it way down here.
Okay, I think a number of people have solutions. So let's go through the solution as a group now, and you can compare your work to their work. Yes, David? Okay, so what's the first thing you do? No crying. Crying's optional. The first thing should be to draw the diagram. Yeah, it's right there, not on your paper. And then once I have the diagram, what do I need to do then?
Set it up in the equation. So you got your work net equal.
Identify work non-conservative.
Yes.
It says assuming no friction. What does that mean to me? No work non-conservative. Yay! Then I identify potential energy starting, kinetic energy starting, potential energy final, kinetic energy final. So let's just do a poll. How many people chose ground level for height equals 0, for elevation 0? No. How many people chose the top of the loop for elevation 0? None. How many people chose the starting height as elevation 0? 1. Well, what the rest of you choose?
I don't know.
You have to choose.
We didn't do the change.
Okay. So Oksana said top of the loop. So I'm going to do what Oksana did, not what David did. Why? Because it's the opposite of what I did in the last example, just so you can see different ways of doing it. Judith.
So I was wondering, how did you know that like it started up there and it's now going sloped into the loop?
Because it says how high above the top of the loop must I start. So that's how I know it's higher. Okay, so assigning y final is 0 at the top of the loop, then what's my potential energy initial? What's the equation for potential energy due to gravity? MGH. So in this case, H is, hey, look, it's H. What's the equation for kinetic energy, or what's the kinetic energy at the top? 0, because it starts from rest. Then potential energy final. What's my potential energy at the top of the loop? 0. What's my kinetic energy final? 1/2 m v final squared, but we know v final. V final is 1.6 rg. It's the square root of 1.6 rg. V final squared is 1.6 rg. Okay, well, I'm going to leave them like this until I get to the end. So I now have broken things up into initial and final kinetic and potential energies. I only have one more step and then it's algebra. What's that last step? That last step is the important step. What's our method for solving this?
Work energy conversion.
Work energy relation. The work non-conservative is change in kinetic energy plus change in potential energy. That is kinetic energy final minus kinetic energy initial plus potential energy final minus potential energy initial. We had identified, as indicated by this circle, that work non-conservative is 0. Kinetic energy final was 1.6 mRg over 2. That's just taking this and putting the 1.6 where the 1 is. Just minus kinetic energy initial, that was 0. Plus potential energy final, that was 0. Minus potential energy initial, mgh. I'm trying to solve this for h. Notice David asked, what is the mass? And I said,
It's not important.
and so what I have is 0 equals 1.6 over 2. Quick, what's 1.6 over 2? 0.8 Rg minus GH. H is equal, oh, notice there's G's in both of them. I can cancel the G's. I didn't even notice that. Cancel those G's. H is equal to 0.8 R. So 0.8 times 14 meters is our answer. There is a square involved, which is 11.2, which I know at least one person. I think that's what Russell asked. Is that right?
We did it totally wrong and still got that answer.
That would be odd. Okay, so somebody talked about the square. The V was square root of 1.6 Rg. So when I have 1/2 mv squared, I'm going to square the square root. And that's where I got just 1.6 Rg from. David had a question.
Is that answer correct? Because it's asking for how high above the top of the loop it has to be.
Okay, part B says if there's no friction, how high above the top of the loop you have to be to have that speed at the top of the loop. And so, yes, that is correct. Part C says, what if there's friction? What are you going to have to do if there's friction?
Make it higher.
You're going to have to start higher. And so for part C, it says it is actually, if it actually starts 6.5 meters higher to achieve that speed, then how much work was done by friction? Now you can answer this in a long way or a short way. I had to raise the elevation by 6.5 meters. If I raise the elevation, in terms of energy, what am I raising? Potential energy. How much did I have to raise that potential energy by? 6.5 meters times G times mass. Now mass is important.
Yes.
So the amount I had to raise the potential energy is equal to the amount of energy non-conservative is going to take away. So I can short circuit this to work non-conservative is equal to additional starting potential energy, which is mg times my 6.5 meters, the additional elevation. And so then I just put in my 1,500 kilograms times 9.80 meters per second squared times 6.5 meters and I have how much energy friction removed.
260,190.
260,000?
Yeah.
That's a lot of energy that friction scrubbed away from you.
Wait, that's it.
Yeah. Because that's how much additional energy you had to start with to end with the energy you wanted.
Okay.
Okay, now a problem with friction. This is, you had a question, Anna? No. This is based on reality, except for I think my coefficient of friction is a little bit off. A person goes down a slide that has an elevation drop of 11.6 meters. This is an actual slide that has an elevation drop of 11.6 meters and a total length of 17.4 meters. This slide has an actual length of 17.4 meters. If the coefficient of kinetic friction is 0.391, which is a number I just chose from another problem that I think is unrealistic, does she make it to the bottom of the slide? And if so, how fast is she traveling when she reaches the bottom of the slide? So I don't think we're going to have time to solve this problem. Let's think about how we would solve it. So what's the first thing you would do?
Free body diagram.
Not free body here, because we're doing work energy method. Just draw a diagram. Draw a diagram, and what shape should you make the slide? Yeah, make it a straight slide. It doesn't tell you what the shape is. So we're going to say, based on what they told me, this could be a potential. So you make a straight slope, and then the answer comes out the same if you do things differently for the most part, unless you stop halfway. You know, if it's like, it goes like this for 5 feet, and then it's flat for a mile, you know, well, yeah, or, you know, then that's not going to work out. But does she make it to the bottom? What condition would keep her from making it to the bottom?
Friction.
Yeah, if friction is absorbing energy faster than gravity is giving her energy. Basically, going back to forces, if the force of friction is greater than the component of gravity pulling down. So I would actually answer this by looking at forces rather than work energy, because that's going to be my key. Then we have, okay, and she easily makes it down. It turns out that the downward component of the frictional force is much bigger. Remember, to get that frictional force, you need the force normal, which means you have to break the forces into components just to get that force normal, no matter how you choose to solve it. If she gets to the bottom, how fast will she be traveling? Well, what is the mechanism you use to get that answer?
You use change in potential and you use the work.
Work non-conservative, which is going to be the force of friction times the length she travels. So you have to calculate what that force of friction is, which means you calculate force normal multiplied by mu, then multiply it by the distance of the slide. That's a negative work because it's taking energy away. And that's equal to the change in kinetic energy, 1/2 mv final squared minus 0 because she starts from rest, plus the change in potential energy, mass times gravity times the final height minus mass times gravity times initial height.
Which the mass cancels out again, right?
The mass indeed cancels out. Mass is in every term. So it doesn't have mass here, and if we had time to do this, I was going to ask you, so, you know, how much difference does it make if she's a large woman versus a small woman? In theory, none. But there are some other things involved. Things like air resistance. Air resistance is going to slow you down as well, right? And if you have like skin touching, you know that friction is going to be much higher than clothes touching. You know, there's a lot of variables there. Just a quick review of what we have here. We have the definitions of of work, kinetic energy, potential energy, and the work energy relation. And then our method of solving problems using that work energy relation. So your homework that's going to be due Friday is going to be on solving problems using work energy relation. That was the hand going up. All right. Have a great Wednesday. You have a question? Yeah.
Oh, wow.
That was so strong.
Yeah, and then for mine, I did that for the first part, and then I tried something else for the second, so I have a 90% on the top one, but I shouldn't, because I got it right.
We're gonna help each other.
Yeah, you take.
Okay, I just, what do you want us to do, like, to finish the problem?
Until one. That's good.
Yeah.
We should get the same answer though.
So like, if you were to,
In this case, the network is not zero, so.
No, you do this one minus that one, and then that would get you that final.
You are out, so one's negative, one's positive.
Check out.
Yeah, because gravity is acting down.
Is that why we got it wrong?
This was mine.
Well, yeah, I thought you know.
This first is 0.
Well, the force of gravity is down, the distance moves us up.
Yeah, because we
So
didn't know
they're opposite directions.
So we got 0. So your first point is 0, 0, then it goes on to.
So what's correct is what you're showing.
I don't know, it must have been something
Oh, you got plenty coming. See, like this one here, started with 0.95, 10. So I think.
Oh, maybe that's why I got it wrong, because we didn't put the negative in.
Stop with you.
And that is a very important factor, right? That's not true.
Oh, okay.
You gotta be there.
Oh, yeah.
That was
We
doing.
don't put this here. Like, we don't include it in the line.
For one note. Cause like I forgot my password for the one that the school made, so I made another account.
But not one from the school. It won't allow me to add off-campus missions for some reason. Talk to Debbie Winchester about how to recover the password.
Oh, like,
I'm sure
which
there's a
homework
password recovery
question?
thing she.
Yeah, there's one that I got right except for a
Is it a
negative,
big building?
and I didn't
Yeah,
know why.
yeah, she is.
It's like the
Or
first
three,
one.
it was
Yeah.
number 3, the farmer with the bucket.
Oh, okay.
Farmer in the